December 7, 1941, Pearl Harbor. United States ship Utah rested in berth Fox 11 off the northwest side of Ford Island. To the casual observer, she was a battleship of the Florida class, but the mechanical reality was far more complex. She displaced 21,825 tons of steel and had spent her early life as a frontline combatant. However, by the morning of the attack, her primary batteries had been removed and her internal spaces had been gutted. She was no longer a vessel of offense, but a high-technology target ship, specifically modified to serve as a mobile laboratory for the development of naval gunnery and aerial tactics. One of the most significant and obscure engineering milestones in her history was her conversion into the first radio-controlled ship in the United States Navy. This modification required the installation of an intricate system of pneumatic and electrical actuators that allowed her boilers and engines to be operated remotely from a distance of miles. This was not a primitive remote control, but a sophisticated integration of 19th century steam power and early 20th century electronic logic. She could navigate and maintain speed without a single soul on board, which made her an invaluable tool for testing the effectiveness of new weapon systems under realistic operational conditions. This mechanical autonomy made her a unique asset, but it also made her internal structure more vulnerable, as many of the traditional damage control features had been altered to accommodate the remote systems. The visual signature of the Utah on that December morning was dictated by what engineers call target ship modifications. To protect her steel decks from the kinetic impact of practice bombs, her horizontal surfaces were covered in 6 by 12-inch timber planks. These heavy wooden timbers were layered across her superstructure, creating a flat and textured appearance that stood out against the standard battleship gray of the rest of the fleet. From an altitude of several thousand feet, this configuration created a lethal optical illusion. The pilots of the Japanese carrier Soryu, looking down through the morning haze, saw the characteristic flat profile of an aircraft carrier flight deck. This was the geometry of deception. The Japanese planners had prioritized the American carriers as the primary targets of the raid, and the Utah in her wooden armor looked the part. When the first torpedo bombers rolled into their attack runs, they were not hunting a retired battleship. They were looking for the high-value targets that usually occupied the carrier berths. The torpedo bombers assigned to this sector released their Type 91 aerial torpedoes with mathematical precision. 2 of these 1,000-pound weapons struck the port side of the Utah in rapid succession. The torpedoes were not designed to defeat a target ship, but to destroy the primary armor belt of a modern battleship. Against a hull that had been modified and lightened for training, the damage was catastrophic. The steel bulkheads were shredded, and the displacement balance of the 21,000-ton vessel was immediately compromised. The ship began to list to port as thousands of tons of harbor water rushed into the gutting of her interior. The timber planks that were meant to shield her from the impacts of mock bombs now became buoyant hazards as the ship started to roll. Within minutes, a vessel that had served as a pioneer of radio control and training was being consumed by a mistake in identification. The strategic weight of the attack was shifting, but for the men on board, the survival was now a matter of navigating an inverted steel maze. The open loop remains, why a ship essentially stripped of its offensive power and converted into a wooden-covered testbed, became a priority target for the most elite torpedo squadrons in the world. 165 degrees is the terminal angle of rotation, achieved by United States ship Utah in the span of only 15 minutes. To a naval architect, this timeline represents a catastrophic failure of hydrostatic stability that is nearly impossible for a standard battleship to replicate. Under normal combat conditions, a battleship is a marvel of counterbalancing weights designed to resist the massive rolling forces of its own guns and the impact of enemy shells. However, the Utah was no longer a standard battleship. Because of the target ship modifications, her primary 12-inch gun turrets had been removed years prior. These massive armored structures weighed hundreds of tons each, and their removal had fundamentally altered the weight distribution of the vessel. By stripping the ship of her heavy, low-slung weaponry, the engineers had inadvertently raised her center of gravity relative to her center of buoyancy. This created a situation where once the hull began to tilt, the gravitational force pulling the top of the ship down was significantly stronger than the buoyant face trying to push the hull back up. When the 2 Type 91 aerial torpedoes struck the port side, they introduced thousands of tons of harbor water into the gutted interior compartments. In a frontline battleship, the internal subdivision and the weight of the main battery would have slowed the rate of the roll, allowing damage control teams to attempt counterflooding. On the Utah, the internal spaces had been cleared to accommodate the radio control equipment and training facilities, leaving large, unobstructed volumes for the water to fill. As the port fire rooms flooded, the ship did not just settle, she began a rapid and irreversible pivot. The 6 by 12-inch timber planks that covered her decks added to the mechanical chaos. As the list increased to 20, then 30 degrees, these heavy wooden beams began to break free from their mountings. In some areas, the timber provided asymmetric buoyancy that acted like a lifting wedge against the submerged deck, while the flooded side continued to pull the hull deeper. The speed of the capsizing created a lethal environment for the sailors below decks. Among them was Chief Water Tender Peter Tomich, who was stationed in the boiler room. As the ship crossed the 45-degree threshold, the floor became a wall, and the heavy machinery began to strain against its mounting bolts. Tomich realized that the rapid inversion of the ship would cause the boilers to lose their water levels, leading to a massive steam explosion. In a high-pressure steam system, if the heated tubes are exposed to air and then hit by a surge of cold water, the resulting expansion is instantaneous and violent. Tomich made the logical decision to remain at his post to manually secure the valves and prevent the boilers from detonating. His engineering foresight prevented a secondary catastrophe that would have likely killed every man in the adjacent compartments through high-temperature steam exposure. By the 10-minute mark, the list had exceeded 90 degrees, and the ship was effectively lying on her side. The hydrostatic pressure was now pushing against the upper superstructure, which was never designed to be a primary buoyancy boundary. The portholes and hatches on the starboard side were now facing the sky, while the port side was buried in the harbor silt. The final 5 minutes of the roll saw the ship rotate another 75 degrees until the hull reached the 165-degree mark. At this point, the Utah was nearly inverted, with only a portion of her starboard bottom and the edges of her gun platforms protruding from the surface. The 6 by 12-inch timber planks that had once disguised her as a carrier were now scattered across the surface of the harbor like industrial debris. The 15-minute capsizing of the Utah remains a definitive case study in how structural modifications can compromise the survival logic of a hull. The removal of the heavy main turrets had transformed a stable battleship into a top-heavy training platform that the ocean could rotate with terrifying efficiency. The ship had achieved a state of stable inversion where the weight of her remaining machinery was now pulling against the harbor bottom. The 58 men lost in those 15 minutes were victims of a ship that had been lightened for the future but was destroyed by the physics of the past. The question for the salvage teams who would arrive years later was whether a 21,000-ton vessel lying at such an extreme angle could ever be convinced to rotate back toward the surface. The salvage of the United States ship Utah presents a logical paradox in the history of naval engineering. Following the successful righting of the battleship Oklahoma, the salvage division of the United States Navy believed they had discovered a universal mechanical cure for capsized vessels. This was a state of supreme industrial confidence where the engineers assumed that two ships of similar hull dimensions would respond identically to the same application of force. In late 1943 and early 1944, the Navy deployed the exact same technical protocol that had functioned on the Oklahoma, but they were treating a patient with a fundamentally different structural pathology. While the Oklahoma was a frontline battleship with her weight concentrated in her armor and guns, the Utah was a lightened and modified training platform. This meant that the mathematical assumptions regarding the center of gravity and the resistance of the hull were flawed from the start. The center of the operation was a mechanical process known as parbuckling. To an elite salvage engineer, parbuckling is the application of radial torque to a capsized vessel to force it to rotate back to an upright position. This is achieved by draping massive steel cables over the high side of the hull and anchoring them to the seafloor or to winches on the shore. For the Utah, the Navy installed 17 individual winches on the concrete wharf of Ford Island. These 17 winches were high-capacity machines capable of exerting millions of pounds of pull. The logic was to use the hull of the ship as a giant lever. By pulling on the cables, the winches would generate the torque necessary to overcome the stable inversion of the hull and pull the ship back through its 165-degree arc of rotation. This mechanical setup required an extraordinary amount of structural shoring and preparation. The salvage teams had to weld dozens of steel turning towers or large triangular frames to the starboard side of the hull, which was the side facing away from the shore. These towers provided the necessary height to ensure that the cables pulled the ship up and over rather than simply dragging it across the harbor floor. Miles of high-strength steel cable were threaded through these towers and connected to the 17 winches. The engineers were essentially building a massive industrial pulley system designed to move 21,825 tons of dead weight. This was the par buckling protocol at its most ambitious, where the goal was to turn the shipwreck into a functioning lever. The difficulty was that the hydrostatic stability of the Utah had been compromised long before she sank. Because her 12-inch main turrets had been removed during her target ship modifications, the weight distribution was no longer balanced for the forces of par buckling. A battleship with its guns intact has a low center of gravity that assists in the rotation process as the weight of the armor belt tries to pull itself back toward the bottom. The Utah, however, was top-heavy even in her inverted state. The engineers had to account for a center of gravity that was now shifted toward the upper decks. This meant that the amount of torque required to initiate the rotation was far higher than what was calculated for a standard battleship. The par buckling was not just a lift, it was a struggle against a ship that had been mechanically hollowed out. As the 17 winches were primed for the first test of the system in early 1944, the engineers were operating under the assumption that the harbor floor would provide the necessary traction. For par buckling to work, the keel of the ship must act as a fixed pivot point. It must grip the silt and sand of the seabed to allow the rest of the hull to rotate around it. If the keel does not grip the bottom, the entire 21,000-ton structure will simply slide. The winches were ready and the cables were tight, but the salvage team was about to learn that the mud beneath berth Fox 11 had a much lower coefficient of friction than the sediment beneath the rest of the fleet. The mechanical gamble was reaching its limit, and the outcome would define the final state of the wreck for the next 80 years. At the precise moment in early 1944, when the 17 winches reached their peak hydraulic tension, the steel cables began to sing with the stress of millions of pounds of force. This was the climax of the par buckling attempt, where the math of the salvage division was supposed to translate into the rotation of the hull. The ship did not remain static, but the movement was not the upward arc the engineers had plotted. Instead of rotating around her keel, the hull of the United States ship Utah lurched laterally toward the shore. The massive steel structure was no longer behaving like a lever, but like a 21,825-ton sled. The salvage had failed because the mechanical resistance of the seafloor was significantly lower than the force required to rotate the ship. The failure is rooted in the specific physics of soil friction and adhesion. To an engineer, the harbor floor is not just a surface, but a critical component of the salvage machine. For a par buckling operation to succeed, the keel must act as a fixed pivot point or a fulcrum. This requires the mud and silt to provide enough soil friction to hold the bottom of the ship in place while the winches pull the top over. At berth Fox 11, the harbor floor was composed of a fine liquid silt that offered almost no lateral resistance. As the tension increased, the suction of the mud was broken by a shearing force rather than a rotational one. The harbor bottom acted as a high-volume lubricant, and the ship began to plane across the seabed. The suction that usually holds a wreck in place was weaker than the pull of the 17 winches, and the ship simply slid into the shore of Ford Island. This lateral slide destroyed the geometry of the par buckling attempt. As the ship moved toward the winches, the angle of the cables changed, reducing the amount of upward torque that could be applied. The turning towers that had been welded to the hull were now pulling at an inefficient angle, and the ship reached a state of mechanical stalemate. The Utah had moved roughly 30 feet closer to the shoreline, but she remained stubbornly on her side. She had transitioned from an inverted state of 165 degrees to a final permanent list of 42 degrees. The ship was now wedged into the sediment at an angle that made further rotational attempts mathematically impossible without a total reconfiguration of the winch farm on Ford Island. The result was a ship stuck in a structural limbo. At 42 degrees, the Utah was neither upright nor fully submerged. A significant portion of her starboard hull and her training gun platforms were now exposed to the atmosphere while her port side remained buried in the mud. The Navy looked at the failed parbuckling and made a cold industrial calculation. The 1944 timeline of the war meant that every salvage asset was needed for the upcoming invasions of the Pacific. The Utah had been cleared from her primary berth, and she no longer obstructed the navigation of the harbor. The cost of a second recovery attempt far exceeded the potential scrap value of her lightened hull. The Navy simply stopped the winches and disconnected the power. The evidence of this mechanical surrender remains visible on the wreck to this day. Because the salvage was abandoned so abruptly, the massive steel cables used in the failed 1944 attempt were never removed. They remained draped over the rusting hull like heavy metallic veins, frozen in the middle of a failed resurrection. These cables are a fringe detail that confirms the exact point where the engineering logic of the salvage division reached its limit. The winches were dismantled and the turning towers were eventually cut away, but the cables were left to the mercy of the elements. The United States ship Utah was left in her 42-degree list, a silent monument to the moment when the soil friction of Pearl Harbor defeated the industrial might of the American salvage fleet. 80 years of immersion in a high-oxygen harbor environment provides a mathematical baseline for the total structural dissolution of a battleship hull. In the shallow waters of berth, Fox 11, the United States ship Utah is subjected to a dual-phase chemical assault that no industrial coating was ever designed to resist. To an engineer, the wreck is a 21,825-ton girder that is slowly being disassembled by the sheer kinetic energy of the tides and the corrosive potential of the salt air. While the internal compartments remain submerged, the starboard side and the training gun platforms are exposed to the atmosphere. This exposure creates a permanent cycle of wetting and drying that accelerates a process known as scantling degradation. Scantling degradation is the systematic thinning of the structural members of a ship through the oxidation of its steel. The scantlings are the heavy frames, the longitudinal girders, and the primary hull plating that provide the structural skeleton of the vessel. For a ship launched in 1909, the steel was manufactured before the era of modern alloying. When exposed to the oxygen-rich environment of a shallow harbor, the iron molecules react with the oxygen to form hydrated iron oxide or rust. This is not merely a surface condition, but a structural failure where the steel loses its thickness and its ability to handle mechanical loads. Every year, the saltwater breaks down the molecular bonds of the 1909 steel, and the once formidable battleship hull becomes a fragile lattice of brittle metal. This atmospheric decay provides a startling contrast to the condition of the submerged sections of the hull, which are subjected to anaerobic decay. Anaerobic decay occurs in environments where the oxygen levels are so low that the standard processes of oxidation and biological breakdown are essentially suspended. Because the port side of the ship is buried deep in the harbor silt, it is protected by a biological shield of fine sediment. This mud acts as an oxygen barrier, preventing the rapid rusting that is consuming the above water sections. Inside the buried compartments, the machinery and the bulkheads are often found in a state of eerie preservation, where even the original paint remains visible. The Utah is essentially a ship of two realities where the rotted top is being slowly eaten away, while the bottom remains a frozen forensic artifact. The exposed wreckage is dominated by the remnants of the 5-inch training guns and their supporting platforms. These mounts were the centerpiece of the target ship modifications, and they were designed to provide anti-aircraft practice for a Navy preparing for the air wars of the 1930s. Today, they are jagged ruins of rusted steel pointing at 42 degrees toward the Hawaiian sky. The teak decking, which once provided a stable floor for the gunners, has rotted away, leaving a mess of rusted frames and broken supports. Despite the structural thinning, you can still see an intact porthole sitting above a section of collapsed plating. This is a testament to the original build quality, where even a century later, the heaviest fittings remain attached to a hull that is literally falling apart around them. The only part of the ship that has successfully escaped this dual-phase assault is the ship's bell, which was recovered during a maintenance survey. This massive bronze fitting now resides at the University of Utah as an isolated remnant of the original mechanical structure. Bronze is far more resistant to the corrosive cycle than steel, and it provides a physical record of the ship's identity that the hull can no longer maintain. Back in berth, Fox 11, the ship continues her 42-degree list into the silt. The scantling degradation is a slow-motion autopsy where the harbor is systematically reclaiming the steel. The ship is a permanent topographical feature, but her structural life is measured in decades rather than centuries. The question for the future is how long the failing steel can support the weight of the memorial walkway before the gravity of the ocean finally completes the work that the torpedoes started 80 years ago. It is a logical paradox that a machine designed for absolute destruction has survived for 80 years as a permanent monument of absolute preservation. The United States ship Utah is neither a functioning vessel nor a fully cleared wreck, but a structural landmark that serves as a tomb for 58 men. This creates a state of permanent harbor residence where the engineering failure of the 1944 salvage attempt has become the foundation for a historical and ethical sanctuary. The ship is a dead girder that remains a vital component of the Pearl Harbor landscape, providing a stark visual record of the day that maritime physics outworked the industrial capacity of the American salvage fleet. The center of this sanctuary is the boiler room, where Chief Water Tender Peter Tomich remains at his post. His decision to stay was not based on a standard of emotional sacrifice, but on a standard of engineering logic. He understood that a steam explosion would be the terminal event for every sailor trapped in the hull. By choosing to stay and manually secure the valves, he was trading his own life for the prevention of a catastrophic expansion of high-pressure gas. This is heroism expressed through a technical risk management. His remains were never recovered, and he continues to serve as the silent engineer of a ship that is now a permanent part of the seafloor. His presence is the reason the Utah was never subjected to the aggressive cutting and dredging that removed other wrecks from the harbor, and it is the reason the failed parbuckling attempt was never repeated. The tradition of interment has turned the Utah into a living record of the attack. Under the provisions of the Sunken Military Craft Act, the ship is recognized as a war grave, and survivors of the attack are permitted to have their cremated remains returned to the hull. This creates a forensic cycle where the ship that saw their combat service becomes their final biological resting place. These survivors are not simply being buried, they are being interred within the scantling degradation of a ship they once operated. As their ashes are placed within the rusted bulkheads, they join the 58 men who have occupied the silt since 1941. This tradition ensures that the ship remains a sacred space where the mechanical decay of the steel is secondary to the preservation of the human signal. The physical interface for this sanctuary is a 70-foot bright white walkway that extends from Ford Island toward the rusting hull. This walkway is a respectful distance from the wreckage, but it allows visitors to see the 42-degree list that has defined the ship for 8 decades. From this vantage point, the failed cables of the 1944 salvage attempt are still visible. These cables are the metallic veins of a failed resurrection, and they serve as a reminder of the day. The soil friction and adhesion of the harbor mud defeated the 17 winches of the Navy. The ship remains wedged in the silt, precisely because the sediment beneath berth Fox 11 refused to provide the traction necessary for the parbuckling to succeed. The United States ship Utah stands as a silent monument to the strategic mistakes and the industrial limits of the Second World War. She was a target ship modified with timber and radio control, only to be destroyed by a mistake in identification and a failure in hydrostatic stability. Today, she is a permanent topographical feature of Pearl Harbor, where the rotted decks and the exposed gun platforms provide a habitat for marine life and a destination for remembrance. The ship is slowly sinking into the mud as the anaerobic decay of the lower hull struggles against the scantling degradation of the surface. As long as the steel remains, the Utah will track the tides of the Pacific, a 21,000-ton reminder that the ocean keeps what it claims, and the most durable memorials are often built from the ruins of a failed engineering gamble.